Let's start doing some calculation. We'll put some things together on this thing on page 23 in a minute. Okay. Let's say I have a hydrogen, an acid, a strong monoprotic acid like HNO3. And the concentration of HNO3 in brackets means the molar concentration is 0.150 molar. Let's find pH. Let's find pH. All right. Since HNO3 is a strong monoprotic acid, when we put it in water, it breaks up completely. Therefore, HNO3's molar concentration is equal to the hydrogen ion concentration. It's the same thing because every one of them break up. Every one of them dissociate. Since pH is equal to the negative logarithm of the hydrogen ion concentration, that's the negative logarithm, in this case, of this number. So what's that going to be? What now? Remember, these brackets mean the molar concentration, so I have to put molarity on this. I need to round that off to how many digits? 3 digits. I got 1, 2, 3 digits here. They're significant. So the pH then should be 0.824. I mean, the pH of, I'm sorry, that's right. pH is, I'll take that back. This is the pH I'm calculating here. So we don't have any units on pH. pH is unitless because you don't put units in the exponent position. Okay, so the pH is 0.824. Okay? It's a pretty low pH. You got to put in 0.150, then logarithm, then change the sign on that smaller calculator. 0.150. The concentration is 0.150.
You don't always give us the concentration.
Well, you have to have enough information, whatever that happens to be. Okay. So 150, then you're gonna hit the logarithm, then you're gonna hit your change of sign here. And that's what you get. All right. Now let's take that and put it on that exponent as an exponent on 10 and see if we get the same number we started with, or pretty close to it. Okay? So if we have a pH that's equal to 0.824, and we want to find the hydrogen ion concentration, then we're going to take 10 and put negative 0.824 on it. Yep. That's right, 0.824. Well, no, the negative is what happens when you put it on this. To undo a negative logarithm, you got to have a negative exponent. All right?
What's the exponent for that last one?
There's no exponent on this number.
So you don't have to, just that was
And when you round that off, you get 0.150 again, don't you?
Now, how did you get, okay, so my calculator, the old cheap calculator, like you said.
Yeah, sometimes you get what you pay for.
I don't know how to do the that's the 10 part.
You can't do what?
I can't do that kind of example.
Bring me your calculator, let's see.
Just do it on the,
Oh, you got one of these? What you doing on this one? Okay, you got to back into the calculation with this too. So we're going to put in, all right, here's your, this is like your up caret here, okay? I think we can do it this way. Let's see if it works. 10, put it on the exponent there, change the sign. Nope, we got to back into it, okay. So 0.824, change the sign, exponent on 10, and get that number. Well, that's not it, is it? Did I put in wrong? Huh? And then put on negative. Oh, okay. There you go. He's got it figured out ahead of me. How about that? 0.824, and then hit the change of sign. Okay. That's the way. That's one way to do it.
Hey, I got it.
Okay.
That was it.
Again, you got to know how to work. Talk to your calculator.
your own.
What?
Got to know how to talk your calculator's language. All right, now. Well, I need to move forward here real quick, okay? Because we've got people to leave a little early and we need to know how to do some calculations for homework. All right. Notice this equation right here on page 26 of your handout. Okay? KW. KW is the auto dissociation constant for water. The auto ionization or auto dissociation constant for water. And that number, that actually has a value of 1.00 times 10 to the negative 14 molar squared. That's the value of KW. Okay, and KW is equal to the hydrogen ion concentration multiplied by the hydroxide ion concentration. Okay, so in this problem we already know what the hydrogen ion concentration is. We have it right up here. Okay, so we can plug in this number for KW. We can plug in the hydrogen ion concentration. And because we have 2 out of the 3 things in this equation, we can find OH. We have to isolate the unknown. And how do you isolate the unknown in this case? Divide both sides by 0.150 molar. No, this is the way to do this right now. And we get rid of one of the molarities here. So when we do that math, we'll have the hydroxide ion concentration. Molar concentration of hydroxide. Alright. Now I want to put the top in parentheses because this is an exponential number just to keep everything kind of straight. Make sure we don't cross up some of our calculations. 1.00 exponent negative 14 divided by 0.150. And so I got a hydroxide ion concentration of 6.66 continuous times 10 to the negative 14 molar. When I round it off. Well, no, when I round it off, I'm going to take off this number here. I need 3 digits. 6.67 times 10 to the negative 14 molar. That's the OH concentration. Okay, remember pH was the negative logarithm of the H, right? Well, pOH is the negative logarithm of this. Which is the negative logarithm then of 6.67 times 10 to the negative 14. We could, but I'm going to move forward from this, okay? And so I get an answer of pOH that's 13.17587417, okay, which I round off to 3 digits, and I get a pOH of 13.2. Yeah, the OH concentration is this. pOH is the negative log of that. All right. All right, here's the last calculation. If I know the pOH, I can find the pH. Because pH plus pOH always equals 14. So we'll put in 14 equals pH plus 13.2. And actually you can say 14 has as many exponents as you want. So I say 14.000 or 14.0. And when we subtract, you get a pH 0.8, right? Well, you subtract 13.2 from both sides.
Where's the 14?
Right there. Okay. Well, what was our original pH a while ago when we looked at it and we got it? About 0.8, wasn't it? Our pH was 0.8, wasn't it? Right? Okay. So you can go and find any one of these from any of the others. So you want to see this page again? Is that what you want? Okay. So this is your homework problem.